Morning, folks. It's me, it's Mr. Tuttle, down here in the office on a Thursday morning. I hope you're all doing well. I'm doing fine, in case you're wondering. Thanks for asking. All right, so we're at the end of this week. This week has been mostly about this concept of momentum. You've worked on momentum and collisions and stuff like that for the last 3 days. Today we're going to move away from momentum for a little bit and talk about three different concepts. Namely, we're going to talk about the concepts of work, energy, and power. Okay. And just like with momentum, just like with a lot of words, these concepts, work, energy, and power, those are words that get used a lot in everyday situations. But of course, when we're talking about these concepts in a physics context, they have very specific meanings. And so let's first talk about the meaning in physics of work. So what is work in physics? Well, let's see. When a force acts on an object and causes a displacement, then you've got work. Then we say work was done on the object. So that's kind of, one way of thinking about the definition of work. When a force acts on an object and that object moves in the direction of the force, then that's work. Okay. So just from that concept, let me just kind of give four common scenarios, and we'll analyze it and decide whether or not work was done in that situation. So let me see. So behind here is a wall, right? And I can push on it as hard as I want, and it's hopefully not going to go anywhere. But let's say I were to push on this wall for like an hour. Well, I'm not going to do it for an hour. So I exerted a pretty significant force on that wall. If I would have done that for an hour, I would have actually gotten tired, and I might say, oh man, that was like some hard work. But was work actually done if I push on a wall, but the wall doesn't move? Well, the answer to that question is, say it with me, no. There's no work done in that situation of me pushing on the wall because there is no displacement. For work to be done, there has to be not only a force, but there has to also be a displacement. Okay, so that's the first situation. Second situation, if I take this marker and I drop it, that was easy. Was any work done in that situation? Well, there was a displacement for sure, right? The marker fell from here to the ground. But was there a force that caused that displacement? And I think you're all saying to yourself, well, yes, of course. It was the force of gravity that caused that marker to fall. And so in that situation of something falling to the ground, there is work being done. The work is being done by gravity. It's causing the displacement down. Okay. Third situation, this one is one of my favorites. Let's say I'm at a restaurant and, I'm trying to hold this level, but I've got this tray that's, got all kinds of food and beverages on it. And I'm walking across the restaurant at a constant speed, holding it level so that nothing falls off. What's happening there? Is there any work done in a situation where I'm carrying something across a room and I'm holding that thing that I'm carrying at, it's not moving up or down, it's only moving side to side? This is a tricky one, right? Because, okay, let's think about it. Is there a force involved? Well, yes. I'm applying a force to the bottom of the tray or whatever it is that I'm holding. Otherwise, it would be falling to the ground. So there is a force, and that force is directed upwards. There is a displacement. The object is moving across the room, though it's not moving up or down. So we have a force, we have a displacement. It seems like we might want to say, yes, there is work being done, but Here's the thing, there actually is not work being done there. And if you're wondering, what the heck, what do you mean, why not? Stick with me for another few minutes and we'll talk about the more mathematical equation for how to determine work. For now, carrying a tray or carrying something across a room, no work being done on that object. Okay? And then, lastly, if you have, any kind of rockets accelerating through space, cars accelerating down the street, you know, yeah, there's work being done in those situations. The fuel that's being emitted out of the back of the ship. I hope all of you got a chance to watch the rocket launch a few days ago. I honestly cried a little bit. It was pretty amazing. It was so amazing. When we talk more about gravity, in the next week or two, we'll talk more about like what is actually involved in a rocket taking off like that and doing what it did. It's pretty fantastic. Anyway, I'm digressing. Yeah, so there's work involved when a rocket accelerates through space. Okay, so let's talk about this mathematical definition now. All right. So work is done if a force causes a displacement, but there is one tiny addition to that, a notion that we need to add so that we can account for situations like the waiter carrying the tray. So really what we have is work, which we'll just use a uppercase W to represent, equals F times D, and then this, cosine theta. So this is like the full sort of concept or a mathematical definition of work. Okay. F, of course, stands for force. And let's not forget that force is a vector. This could be positive, this could be negative, which means there is going to be situations where we've got positive work and we have situations where we have negative work. Okay, we'll talk more about that later. D is the displacement. That is not a vector. Remember, well, wait a minute. Oh yeah, it can be. So you're right. It can be positive or negative depending on the direction that it's moving, right? But here, this is the new thing. What is the theta involved in this equation? Well, the theta involved here, this is the angle between the force and the displacement. Okay? That is the angle between the force and the displacement. So let's we'll get into like using this equation a little bit, but first I want to focus a little bit more on this theta situation. So I'm going to try to draw some pictures. Here's the first one. Let's say that is it's a box on wheels. I don't know. And this is me. And I am pushing on this box that has wheels on it, and it's going to move. The displacement is going this way. My force is going the same way. And so if you think about it, those two vectors, right, those two arrows are pointing in the same direction. And so we would say that if they're pointing in the same direction, then the angle between those two vectors is 0. Right? 0 degrees. And if you remember, or if you type cosine of 0 into your calculator, you will find that the cosine of 0 equals 1. So what does that mean in terms of this equation? Well, what that means is, well, if I'm pushing horizontally and the thing is moving horizontally, then all of the force that I'm applying to that object is contributing to the work that's being done. Right? So that's the kind of role of this theta here is to help us see and be able to quantify how much of the force that I'm applying is actually contributing to the work. Okay? Another situation is, well, what if, let's say, I'm going to keep the same picture in the same scenario, but let's say this box is actually moving towards me, and I am pushing against it, okay, so now the displacement is pointing to the left, and the force that I'm applying is pointing to the right. You can imagine what's happening here is that force that I'm applying, right, is giving an impulse to it, right, and I'm doing work that's going against the motion of the object, okay. What's the angle between those vectors? Well, the angle between those vectors, if one is pointing to the right and one is pointing to the left, the angle in that situation is actually 180 degrees. Okay. And again, if you were to enter this into a calculator, or maybe you've had a little bit of trigonometry and you know this, but the cosine of 180 degrees is -1. Okay, so it's the exact opposite scenario but before. What that means is all of the force that I'm contributing to the situation is gonna sort of do negative work on that object. Okay, so those are kind of two extreme situations. So there's one more sort of extreme situation, and that is the situation where here I am. Okay, that's a bunch of food on a tray, and I am moving to the right. Okay, the force I'm applying is pointing up. And so we think about these two vectors and say, well, what is the angle between these two vectors? Well, if one is pointing to the right and another one is pointing up, then in this situation, theta is actually 90 degrees. And the cosine of 90 degrees equals 0. If you don't believe me, put it in your calculator, but I've been doing this for a long time. Cosine of 90 is 0. So what does that mean? That means even no matter how much force I'm applying, no matter what the displacement is, the cosine of 90 is 0, so all of this becomes 0. There's no work done because the force isn't moving the object, right? This force isn't moving the object, something else is moving the object, okay? Okay, so I think that, let's see, am I missing anything? Those are my notes. So one more situation. So those are the extreme scenarios, right? When theta is 0, when theta is 180, and when theta is 90. But a lot of times we have situations like this where, let's say that's a box, okay? And I want to move this box. And so what I do is I tie a cable to it or something, and now I'm standing up here. For some reason I've gotten much bigger, and my arm is pulling. This is a great picture. So I'm pulling on this box, and the angle that rope makes is something like 30 degrees, okay? The box is moving straight horizontally, okay? And so what's the situation here? Well, if the force is going that way, the displacement is going horizontally. In this situation, theta is equal to 30. So it's not like all of the force that I'm applying is contributing to the work. It's only the portion. It's only like that part, right? So it's just the cosine of 30 degrees. So the rest of it, right, there is another component of the force that's going vertically, but that doesn't count here because it's, that vertical is 90 degrees to the actual displacement. None of that is contributing to the actual work, unless the box actually lifted off the ground. In that case, and we'll look at some situations like that, there is two different kinds of work happening, one vertical and one horizontal. So, okay. All right, I think that's good for now. I'm going to pause this video and go grab some coffee, and then we're going to do a few kind of practice problems, and then I think we'll be good for today. So I'll see you in just a minute. Cheers.